Hello everyone, my name is Wang Renqing and I'm a student of Chemical and Biological Engineering in Hong Kong University of Science and Technology. Today I'm going to introduce the iron doping graphite carbon nitride. So this poster might, might be a little bit different from other posters of this course because it's based on a project that I have done before, and most of the figures and the data are from my paper. Due to their interesting electronic properties and their promising catalytic activity, stable and cheap polymer semiconductors such as graphite carbon nitride have attracted more and more attention. The increasing shortage of energy and environmental pollution have become the main problems in the current social development. So research and development of new clean energy is a current research hotspot. Graphite, graphite carbon nitride is a conjected system, and its basic structure unit is a layer of either triazine or heptazine cores consisting of carbon and nitride atoms. So the valence band is 1.35 electron volts and the conduction band is minus 1.31 electron volt. So it meets the theoretical conditions of photocatalytic hydrolysis. So the band gap is 2.66 electron volt. It can absorb the solar spectrum less than 475 nanometer. But its photocatalytic efficiency has been limited due to the carrier recombination. So in this poster, different metal ions such as the ferrium, the cobalt, the nickel, the manganese, the cerium are doped in graphite carbon nitride to improve the carrier utilization efficiency and the microstructure. Here is a methodology. This flowchart is the precise I followed. First is a sample on a synthesis. I use a thermal polarization of nitride and cerium in tube furnace. I use different nitride and a different amount of nitride to compound a different sample. After that, XRD and EDS are used to determine whether I successfully compound the targeted materials. If not, I do the synthesis again and try to find whether it is a mistake or a fact. Then is a photocatalyzed performance test. Gas chromatography is used for gas flow detection, and I use a 300-watt high-intensity discharge with visible light filter as a light source. Also, I use silver as a donor to measure the oxygen evaluation rate. You may ask, why don't measure the hydrogen evaluation rate? Because some of the doping catalyst band gap is too narrow, and the conduction band is no longer meet the requirement of producing hydrogen. So I use oxygen evaluation as a uniform criteria. The next step is further characterization. Besides XRD and EDS, the SEM and TEM are used to gather a microgram of samples, and the BET is used to find the pore size distribution and calculate the specific surface area. And the absorption spectrum is used to study samples' light absorption property and use the data to draw the Mott Schottky curve to calculate the valence band and the conduction band. For those samples with good performance, I will do further research by doping platinum in them and do the characterization and test. The result of that part is not included in the poster because there is not enough area in my poster. As for results, M means different doping metal, and 20 and 400 and the amount of nitride used for synthesis. M20 is a low concentration doping, and M400 is a high concentration doping. So the high concentration doping samples basically have lower specific surface area. Although cerium-20 has relatively high specific surface area, its performance is not that outstanding. Obviously, the high concentration doping samples have much better performance compared to the low concentration doping samples. You can see that in the chart below. Here is the SEM images for different samples. The low concentration doping samples are regular layered stacking like graphitic carbon nitride, and the high concentration doping samples are amorphous compact stacking. Here I just pick one absorption spectrum for showing. An M20 has obvious tangent line, but for M400 it's not so obvious. So this means that M400 might have multiple energy bands. Those are calculated conduction band and valence band on the right. For some high concentration doping samples, their conduction band is no longer meet the requirements of producing hydrogen, which shows smaller than minus 0.4 electron volt. So that's why I measure the oxygen evolution rate. Then is the discussion part. Actually, I have discussed a little bit while showing the results. So the high concentration doping samples show up very superior in performance compared to the low concentration doping sample rate. Here are some explanations supported by characterization results. First, high concentration of doping brings a material more doping level, or even from continuous band. The band gap is reduced and the photoelectrons are easier to form, so the carrier density is higher. At the second, higher doping could form more doping structure and defects, which could be induced to the uneven distribution of regional space charge. So the separation of holes and electrons is promoted. Thus, the carrier efficiency is higher. And third, metal doping structure on the surface of the catalyst may be used as a co-catalytic active site for oxygen evolution rate. So the high concentration doping samples have more catalytic active sites. Then is a brief concluding. There are some inspirations I got from the experiment. So the metal doping does work, but the doping concentration should be concerned, because higher concentration may increase their properties but influence material structure and decrease specific surface area. So the key point is to find the appropriate doping concentration. And the last part is a reference and their contradictions. I found in Lewis paper, I found that the evolution rate of hydrogen is not twice as oxygen, and the reason is not mentioned. I think the power of the lamp is really high, so the experiment temperature is also high. So some catalyzed may be oxidized. That may be the reason. And in other papers, including my paper, only one side of the samples data is used to do the illustration. So I have to admit that the contingency cannot be avoided. That's all. Thanks for watching.